Hello everybody. Today we're going to look at a second periodic trend. It is called ionization energy. And if you look at the definition, ionization energy is the energy required to remove the most loosely held electron from the outer energy level of an atom in its gas phase. If you look at the equation, you can see that this represents a generic atom. The G is that it's a gas. And in order to remove an electron, there's some energy required, and that energy is called ionization energy. So if I get any atom and remove an outer electron, that atom will now become an ion. In fact, it will become a cation. It will be positively charged. It will still be a gas. And the electron that was removed is represented here in this part of the equation. Now, this energy is measured in units called kilojoules per mole. And what I'm going to show you in a moment is that you're not limited to just removing one electron. You can remove a second or a third. The energy required to remove that first electron is called the first ionization energy. If you remove a subsequent electron, the second one would be called the second ionization energy. If you remove the third, it will be the third ionization energy, etc. So what we're going to do is we're going to take, a regular atom in the gas phase, okay? And let's say it was an atom such as, let's look at something simple like lithium. Here's the nucleus. The first energy level has 2 electrons, and then the third energy level, or the second energy level, has 1. The energy needed to remove that electron is called the ionization energy. So we'll call it IE. Okay, we're going to call it the first ionization energy. And as a result, in this case, lithium is our atom in the gas phase. The atom will now become an ion. So lithium will become +1. It'll still be a gas. And the electron that was removed is shown over here. So that would be an example using lithium. Now, what I'm going to show you is an example where multiple electrons are going to be removed. And before I do that, I'm going to explain eventually the patterns. Okay, if you look at this periodic table, just like was shown with atomic radius, you'll notice that as you go down a group, the ionization energy decreases. What that means is that it takes less energy to remove an outer electron, and we're going to explore the reason behind that. We're going to see why ionization energy decreases. And if you look down here, as you go from left to right along a period, you'll notice it says that ionization energy increases. That means it takes more energy to remove an electron, and we're going to see the reasons behind that. So let's go back for a minute, and we're going to use aluminum as an example, okay? What I'm going to show you now is that you are not limited to only removing one electron, okay? Aluminum has 3 valence electrons, and what I'm going to do is I'm going to show you how to remove each one, all right? So we'll start with aluminum as a regular atom. Okay, aluminum has a total of 13 electrons. It has 2 in the first energy level. It has an additional 8 in the second energy level. And then in the third energy level, it has 3 valence electrons. So let's do this. Let's remove the first one. The removal of that first electron is known as the first ionization energy. And according to studies, approximately it takes 577 kilojoules per mole to remove that first electron. Okay? Once that electron is removed, aluminum becomes Al plus 1. So we just removed the first electron. Now, I'm going to continue doing this process. Okay, I'm going to now get aluminum plus 1, and I'm going to remove a second electron from it. Since I'm now removing a second electron, this is called the second ionization energy. And as a result, aluminum will now have 2 electrons removed. If we go back here, you'll notice how it takes more energy to remove the second electron. It's no longer 577 again, okay? It takes 1814, so let's put here 1,814 kilojoules per mole to remove that second electron. So what I'm trying to show you here is there's a pattern. When you remove the second electron, it takes more energy than it did to remove the first. Now this trend continues. Let's say that I wanted to remove another electron. I've already removed 2. Let's go after number 3. This is called the third ionization energy. And you're going to notice that when you remove the third, the amount of energy increases even more. It's 2,742, okay? 2,742 kilojoules per mole. So notice how the trend continues. Now, here's where it gets interesting. If you notice, okay, I'm going to go ahead and remove a fourth. And aluminum will become plus 4. Now let's go back for a minute over here. Let me go the other way here. If you look here, then I'll take you to this. This is a chart that has the ionization energies of various elements. Now we were focusing on aluminum, which is right over here. And this is the first ionization energy. This rounded it to 580. I know we wrote 577. This is just a rounded version. This is the second ionization energy. Notice it says here for aluminum it's 1815. We had said 1814, more or less. The third ionization energy is 2,740. Now, I don't know if you realized, but aluminum has 3 valence electrons. Let's look at this drawing again. We removed here the first. Okay. Then we're going to remove a second. Then we're going to remove a third. By the time you remove number 4, notice that the fourth electron is no longer in this outer energy level. It's here in an interior energy level. Okay, in order to remove this electron, this is what is called a core electron. The valence electrons are the ones in the outer energy level. The core electron is in an interior level. Look what happens when we go after number 4 for aluminum. Notice that the energies mainly kind of doubled, okay? More or less, it's not a perfect science. Notice that kind of doubled, just a little bit over doubling. This is about the same, but look at this huge jump. There's a reason for this. You would have expected maybe to be between 5,000 and 6,000 kilojoules per mole if you kept following the pattern. Notice there's a huge jump. And here's the reasoning for this. When aluminum goes from the third to the fourth energy level, you are now taking an electron from a core electron. We've already taken out 3. We're about to take the fourth one out. So this electron's being held very tightly. But because it's a core electron, it's actually closer to the nucleus distance-wise. The closer the electron is to the nucleus, the more tightly it's being held. The more tightly the electron is being held, the more energy it takes to remove it. So anytime you jump from a valence level to a core level, you're going to notice that there's a huge jump in the amount of energy required. Okay? I can show you the same example. If you look here, we can look at magnesium. Okay? Notice that magnesium has 2 valence electrons. So when you take away the first valence, it requires 735 kilojoules. When you take the second valence, see how it kind of doubles? 1,445. But when you take out a third electron, it's now a core electron. Notice the huge jump. Okay, you would expect it maybe to be between 3 and 4,000. It jumps significantly higher. So that's another pattern that I want all of you to see, that when you're going from a valence to a core, there's a huge jump in energy. Okay, and this chart is showing you that everything that is shown inside this zigzag line that you see here is that element transitioning from a valence to a core. Okay, if you recall, sodium only has one valence electron. So the minute you remove sodium, the second one's already a core electron. The example we saw earlier had to do with with aluminum that had 3 valence. And after we removed the 3 valence, the fourth one was a core. So that's another pattern that I want all of you to see. Okay, so you are not limited to removing one electron. You can remove more than one, but every time you remove an electron, it takes more energy to remove a subsequent electron. And then there's a huge jump when you go from a valence to a core. Now, let's take a look at the patterns again. There's a reason why ionization energy increases going from left to right, and there's a reason why it decreases going up down. Okay, we're going to go over both of these reasons. Let's take a look at the reason why it decreases going up down. If you recall, elements, and we'll take the elements from period 1. Hydrogen is a small element. It only has 1 electron. In fact, all the alkali metals, including hydrogen, have just 1 valence electron. So here's hydrogen. Here's lithium. Lithium has 2 energy levels. Okay, let's put the valence electron there. Then let's go with sodium. Sodium has 1, 2, 3. There's the valence. And let's put here potassium. And let's go here 1, 2, 3, and 4. Now, there are 2 reasons why ionization energy decreases. Reason number 1 is distance. Okay? Notice the distance between the nucleus and the valence electron, and I'm writing it here so you can see this. We know that atoms get bigger as they go down a group. But what is holding these electrons, what's keeping them from leaving, is the attraction between the protons in the nucleus, right here in the middle, okay, and the electron out here. There's an attraction. However, as atoms get bigger, notice that the distance between the protons and the electrons increases. As the distance gets bigger and bigger and bigger, or larger, the attraction actually decreases. Think of 2 magnets, and as you separate the magnets and you put the magnets further from each other, they're not attracting as well. The closer you bring the magnets, the more they want to attract. As atoms get bigger, their distance between those protons in the nucleus and that electron, physically the distance becomes so great that the attraction decreases so much that electron is easier to remove. It takes less energy to remove that electron. Now, distance is not the only factor here. There's another factor called the shielding effect. Okay? The shielding effect occurs as atoms get larger and larger. You got to remember that inside these other energy levels, let's look at potassium here for a minute. There's a bunch of other inner electrons. We just learned a few minutes ago that those inner electrons are called core electrons. Okay? And the larger that the atom becomes, the more core electrons, the more inner electrons the atom possesses. These core electrons, what they do is they actually provide what is called electron repulsion forces. And what they do, and I'm going to try to explain this so you could understand, these electrons literally shield the outer one over here with the protons in the nucleus. It's like trying to talk to someone in the back of the room and you're trying to have a conversation and there's a bunch of people just walking, back and forth while you're trying to talk to someone at the end of the room. All of these inner electrons are moving back and forth, and what happens is their movement, their presence decreases the attraction between this electron and the nucleus. When that attraction gets further weakened, it allows this electron to be removed much easier. The combination of the distance increasing and these inner electrons, these core electrons, causing the shielding effect, both of those contribute to causing this electron to be removed much easier. So what happens is, as a result, as you go down the periodic table, the electrons are easier to remove because the electron is not being held as tightly by those protons in the nucleus. That is why the ionization energy decreases as you go down. Now, we're also going to take a look at what happens when you go from left to right. Okay, if you look here, notice, let's erase this part here. If you recall from atomic radius, atoms actually are getting smaller as you go from left to right. And the reason, what we discussed, is there is something called effective nuclear charge. And what effective nuclear charge means is that the number of protons increases from left to right. So as the number of protons increases, it actually causes the atoms within a period to get slightly smaller. Now I want you to think about what I said about distance. If atoms are getting smaller as you go from left to right, that means that the electron is held closer to the nucleus because the atoms are smaller. So when atoms are smaller, those valence or outer electrons are actually physically closer to the nucleus. The closer they are to the nucleus, the more energy you need to remove that electron because they're being held more tightly by those protons. I don't know if you saw this relationship, but there's an inverse relationship between atomic radius and ionization energy. As the atoms get bigger, the ionization energy gets smaller. Because as atoms get bigger, you'll notice that the electrons are physically further from the protons, so they're easier to remove. They're not being held as tightly. As an atom gets smaller, which is what's happening from left to right along a period, those electrons are physically closer to the nucleus, and therefore they're being held more tightly. They're being attracted more by those protons in the nucleus, and if they're being held more tightly, that means it requires more energy to remove it. Therefore, as atoms get smaller, which is the atomic radius, the ionization energy actually gets bigger. So that was an inverse relation that I wanted you to see between the two. Okay? So, as a summary, remember that going down a group, ionization energy decreases, which simply means the electrons are easier to remove. Whereas going from left to right along a period, the ionization energy increases, which means it takes more energy to yank that electron out of there. Now, one more thing. This is another trend. This one's going to be a little easier to explain. And if you recall, this is color-coded. You'll notice that with the exception of hydrogen, the metals are on the left side of the periodic table. And then you see the zigzag line right over here. Okay? You could see, there we go, that there are some purple elements there. Those purple elements are metalloids, also known as semimetals. And then on the right side, as well as hydrogen, those green elements are nonmetals. So there's another pattern that you can see here on this chart Notice it says that when you go from left to right, you can see this on the bottom, it says metallic character increases. That means that when you go from left to right, you become more metallic. For instance, you can clearly see that if you are going over here, let's say period 4, notice on the left you're a metal. As you're going to the right, all of a sudden you become a semi-metal. By the time you get to the end over here, you're a non-metal. So as you're going from left to right, you're becoming less metallic. You're becoming more non-metallic. So if you were asked, who is more metallic? Let's say calcium or nickel. Now they're both metals, okay? But if you have to pick who's more metallic, calcium would be more metallic because it's further to the left, even though they're both metals, okay? So that's what happens when you move along a period. You become less metallic when you go from left to right. Now, let's take a look at what happens as you go down a group. The best example would be, let me pick right here. Notice that when you're at the top, when you're carbon, you're a non-metal. As you go down, all of a sudden now you're a semi-metal. By the time you get to the bottom of that group, you're a metal. So what that's showing you is that as you're going down a group, you're actually becoming more metallic. And you could see that here where it says that going down a group, metallic properties increase, or you become less non-metallic. I think it's easier if you learn it as metallic. You become less metallic as you go up down. So let me use an example here. Let's say we were comparing copper versus gold. Now notice copper and gold are on the exact same group. Okay, they're both metals, but if you had to pick which one of the two is more metallic, then you got to remember that as you go down, the more metallic they become. So in this example, gold is going to be more metallic than copper. So this is a third periodic trend that we have seen. We have now seen atomic and ionic radius, which follow the same pattern. Then you saw ionization energy, which is inverse to atomic radius. And now this third periodic trend has to do with metallic character. Okay, so in summary, as you're going down a group, you'll notice that metallic properties do increase. The best way to remember that is just keep this in mind here. And then as you're going from left to right, and this one's pretty easy to visualize because the metals are on the left, the non-metals are on the right. As you go towards the right of the periodic table, you become less metallic. So metallic character decreases from left to right. The only one that is on the left side is hydrogen. Even though hydrogen is a non-metal, it's placed there because it has some common properties with the alkali metals in terms of it having one valence electron. So I hope this helps.